Okay, I am back in black, and this will be a revised lecture on the ratio test and power series. It will replace the original video, which I made a couple of years ago, because since then, I have liked to approach this material in an ever so slightly different way, which I believe both makes the ratio test more intuitive and, once you get used to it, easier to use, because it eliminates the need to have all of the god-awful fractions within fractions that tend to appear when you do it in the traditional way. But we'll see both ways here too, so if you are a traditionalist, that's fine, you can still watch the video. But enough of the prelude. We are about to study our last major test for convergence, the ratio test, which is, in fact, intimately related to the first test we ever learned to distinguish convergent from divergent series, namely the test we learned to distinguish convergent geometric series from divergent geometric series. And do you remember those carefree early days when everything was simple? We would have a geometric series like this, where we would begin with some constant term a, and then to get to the next term, we would multiply by some constant multiplier m, and to get to the next term, we would multiply by m again, and on and on and on, all the way out to infinity. And the test that we used that allowed us to determine whether any given geometric series converged or diverged was simply to look at that constant multiple m. In particular, we looked at its absolute value. And if that absolute value was less than 1, we found that the series converged. And if the multiplier's magnitude is not less than 1, then the geometric series diverged, and that's all there was to it. So that was very, very simple and comforting. And that is why everybody loves geometric series. Although a few people watching this may be slightly uncomfortable and think, wait a second, I thought we call this multiplier r. Why are you calling it m? You can call it any damn thing you want to. I have decided to call it m because it is a multiplier, and multiplier begins with m. Nothing deeper than that. But still, you might say, well, why do most people call it r? Is it just some weird old tradition that nobody understands? No, that's not it. I mean, it is a weird old tradition, but we understand it. The r that people usually use stands for ratio. But when you look at this kind of thing, you usually don't think about ratios, you think about multiplication. Now you can, if you kind of stand on your head and squint one eye, see ratios here. You could think of this value not as the thing I multiply by to get to the next term, but as the ratio of each term to its predecessor. So for example, if we looked at the ratio of this term, m squared a, to ma, in other words, m squared a over ma, we would be left with m. So we could think of that as a ratio. Or again, we could say, if I take the ratio of this term to its predecessor, then I get m cubed a over m squared a. That's m. Well, look at that. The term to predecessor ratio is the same every time. It's always m. So I could think of that as a ratio and call it r. Well, yeah, sure you could, but my God, it's easier to think of it as a multiplier. So let's just do that. And in fact, I think the vast majority of the trouble people have with the ratio test would disappear if it had a better name. If it were up to me, but it isn't, we would rename the ratio test the multiplier test, because as you will see, it is in fact a test about multipliers. But of course, it is not up to me, and there's no point hoping we can change the name at this point. So ratio test it is, but as we will see, it is all about multipliers. In fact, what is the ratio test? Let me just describe it to you without writing it down formally. The ratio test is something we can use for series that are not geometric, but which look more and more and more geometric the further you go into the series. And as we know, the convergence or divergence of a series only depends on what happens in the tail of the series. So if the series becomes effectively indistinguishable from a geometric series in its tail, we can use a modified version of our good old geometric series test to determine whether that non-geometric series converges or not. And that is precisely what the ratio test, which should be called the multiplier test, will do for us. It's essentially testing to see whether a series becomes geometric, or at least so close to geometric that it is indistinguishable from a geometric series in the long run, in the tail of the series. So I think it is high time that I give you a concrete example of the sort of series that I'm talking about, the kind of series that starts to look geometric in the long run. So let's look at this series, where the terms are fractions, the numerators of which are squares, and the denominators of which are powers of 3. So if we were to write down the general term here, it would be n squared over 3 to the n. Now this series clearly is not geometric. In other words, if we think about the multipliers we need to get from one term to the next, they're not always going to be the same. They're going to be changing. For example, to get from 1/3 to 4/9, what would we need? Well, let's see. We need a 4 upstairs, and we need another factor of 3 downstairs. So we would have to multiply by 4/3. But if we multiply by 4/3 again, we would get 16/27. But that's not our next term. We have a totally different multiplier to get from the second term to the third term. What multiplier would we need? We could get it by doing the division, divide this thing by that thing, but I think it's actually useful to just try to think about it in terms of multiplication. What must I multiply 4/9 by to get 9/27? I guess one way I could do it would be to first multiply by 9/4, which would turn this into 1, and then multiply by 9/27, which would get me where I wanted to go. And then, of course, I can clean that up. I've got a factor of 9 upstairs and downstairs, so that becomes 1 and 3, but 9 over 3 is 3. So my multiplier in this case, putting that together, is 3/4. And we could ask the same question. What do I have to multiply 9/27 by to get 16/81? Well, you could do the same trick we did last time, or you could make up your own kind of trick. There's a million ways you could do it just by thinking about multiplication itself. For example, I could say, well, look, clearly on the bottom, I have to multiply by 3. So let me just go ahead and put a 3 in there. And then to get from 9 to 16 upstairs, well, of course, I could multiply by 16/9. So I have 16/9 divided by 3. And when I do that division, I get 16/27. But the point is clear. This is not a geometric series. We get a different multiplier each time. However, these multipliers themselves, even though they're all different, if we were to continue this game all day long, and I don't recommend it, we would find that they themselves are actually approaching one definite value. And as I said, you could spend an hour coming up with these things and you would get a pretty good feel for what that definite value is, but far better just to think about it analytically. Don't think about the individual multipliers, get from the first to the second term, or the second to the third, or the third to the fourth. Think about it in general. If I'm going from this term right here, my general term, to the next term, what multiplier would I need? Well, it will help if we imagine what that next term would look like. After a while, we'll just do this mentally, but this time, let's actually write down what our thought would look like. The next term in the series, of course, would still be a fraction, but instead of n squared, we would have n plus 1 squared. And instead of 3 to the n, we'd be increasing that exponent by 1 to give us 3 to the n plus 1. We've just replaced the n's with n plus 1s. Anyway, what would the multiplier be to get us from this general term to its successor? Let's think it through. Well, we've got this fraction, and we're turning it into this fraction. Of course, we're going to be multiplying by some fraction. The bottom is the easy part. Downstairs, we're going from 3 to the n to 3 to the n plus 1. We have n copies of 3 here and n plus 1 copies here. So we get from here to here simply by multiplying by 3. So I know I'm going to need a 3 downstairs. But what about upstairs? That's a little trickier. We want to go from n squared to n plus 1 squared. There's not just a simple one-step move like we did before to get there, but it's easy enough if we understand how multiplication works. We're trying to get an n plus 1 squared upstairs. So of course we are going to need an n plus 1 squared in our multiplier upstairs. But we also have to get rid of this n squared that's upstairs. So that means I will need an n squared downstairs to cancel it out. And if we multiply n squared over 3n by what I have up here in green, we will in fact get to our next term. So this is our multiplier. Thinking like that takes a little bit of practice, but you'll pick it up quickly. Just to be clear, in case anybody is struggling with that one, let me write it out down in the basement a second time. We were trying to think about what the multiplier should be that will take us from here, n squared over 3n, to this guy, the square of n plus 1 over 3 to the n plus 1. If I write it out horizontally like this, I think you'll see it more easily. We can think about this in terms of our multiplier being a fraction. That will make it very easy. The bottom is a piece of cake. Like we said before, I don't think anybody has trouble seeing that we need a factor of 3, so that we get 3 to the n times one more copy of 3 gives us 3 to the n plus 1. Upstairs, what do I need? I want an n plus 1 squared upstairs. So I can just put an n plus 1 squared upstairs. But if I left that there, of course, I would end up with n squared times n plus 1 squared. I don't want that. I have to get rid of this n squared. But I can do that by burying another copy of n squared down here. That guarantees that I get cancellation of the n squareds, and all I'm left with is the n plus 1 squared upstairs, which is what I want. Make sense? I hope so. As I say, you'll get used to this in no time, but it really helps, I think, to think this way, where we're thinking just in terms of what do I need to multiply by to get to the next term. Okay, well, we now have this general expression for our multiplier in this non-geometric series. It tells us what the multiplier will be at every stage. For example, when n is 1 in this multiplier recipe, I get 1 plus 1 squared, which is 4, over 3 times 1 squared, which is 3, 4/3, which is that first multiplier right there. When n is 2, I get 9/12, which is better known as 3/4, which is indeed our second multiplier. And when n is 3, we get 16 over 27, which is our third multiplier. And so this immediately tells us what all of those multipliers will be, no matter how far we go down. If I want to go from the millionth term to the million-first term, all I have to do is let n be 1 million. But I said earlier what we're interested in is what happens to this general expression for the multiplier as we go deeper and deeper into the series. But we can see that now. What we have is that the multiplier is n plus 1 squared over 3n squared. And in fact, remember when we talked about geometric series, what we were interested in is not really just the multiplier itself, but the magnitude of the multiplier, the absolute value of the multiplier. So let's go ahead and think about the absolute value of that multiplier. That's how we can relate it to our old work on geometric series. Anyway, what is this thing? Well, I could clean it up a little bit. Oh, first let me haul you back into the dungeon here to remind you of a few things away from prying eyes. Some basic properties of absolute values. Hopefully you remember, but maybe you need a little reminder. The absolute value of a product is always the product of the absolute values. And similarly, the absolute value of a quotient is always the quotient of absolute values. It does not work with sums or differences, but everything is fine with multiplication and division, which is where we will need it most. We'll use those properties frequently and often without even explicitly mentioning them, but I will try to be explicit about it the first few times so you understand exactly what's happening. Anyway, if I'm trying to tidy this up a little bit, I could think of this thing as 1/3 times all of this stuff. So I've got two factors. The first one is 1/3, the second one is all of that junk. But when I have the absolute value of a product, I can break it into the absolute value of the two individual factors. So I could rewrite that thing as the absolute value of 1/3 times the absolute value of all that other stuff. Now again, everything I'm doing this first time, after you've done it 2 or 3 times, you just do it in your head and write down the result at once. But there's no harm done in slowing down and reminding yourself what is justifying every move you make, at least the first few times. Anyway, the absolute value of 1/3 is obviously just 1/3 because it is a positive number, so I can remove those. And I can clean up this stuff too. Of course, everybody knows that the quotient of 2 squares is the same as the square of the quotient. Oh, and then, of course, anything squared is non-negative. So these absolute values, in fact, are redundant, because you square anything and you get something that's positive, or maybe 0, but definitely not negative. So it is already its own absolute value. So what we have is that the absolute value of the multiplier, the general multiplier in this series, is given by this algebraic expression, which again just tells us what the individual multiplier would be at any stage. But as I've said a few times now, we are interested in not any given stage, but what happens in the long run to the multipliers. So what we're looking at here is a limit. We want to know what happens to all this junk in the limit. Well, the 1/3 just sits there. It doesn't depend on n. But as n goes to infinity, this stuff inside the parentheses, of course, goes to 1. Trillion and 1 over a trillion, it's effectively 1. So this piece goes to 1. Squaring the 1 keeps it at 1. And when I take the limit, this whole thing goes to 1/3. So what can we conclude from that? What is that telling us? Not in terms of some algorithm, but just thinking logically through this stuff. Well, we have this series. It's not geometric. We get a different multiplier at each stage. But in the long run, if we go deep out into the series, that multiplier in absolute value is getting closer and closer to a third. In other words, we might again imagine what this series is going to look like in the long run. It starts like this and continues on for a long time, and eventually, if we look deep, deep out, thousands, millions, trillions of terms out, whatever you like, we get to some term, I'll just call it star. And then what's the next term going to be? Well, since the multiplier is getting closer and closer to a third the further and further we go out, the next term is going to look like 1/3 of star. And the term after that is going to be basically a third of that term because the multiplier is getting close to a third. So the next term would be 1/3 of star, 1/3 squared star, 1/9 star, however you want to see it. And the term after that would be 1/3 of star, and so on to infinity. And remember, this is all happening in the tail of the series, which is where convergence is determined. So put this all together. We have a series. Its convergence is determined in the tail of the series. What happens up front doesn't affect convergence. But here, deep in the tail of the series, where convergence is determined, the series is indistinguishable from a geometric series. And in particular, a geometric series where the multiplier is 1/3. So what does that tell us about our original series? Well, our little stick figure knows it converges. And that is that. It's a neat argument. I hope you liked it. And if you understood it, you are already most of the way towards understanding the ratio test, because all the ratio test does is basically formalize the argument that we gave right there. So let's go ahead and state the ratio test formally. The ratio test works as follows. Given a series, we find an algebraic expression for the multiplier that takes us from a general term to its successor, and we take the limit of its magnitude, that is, its absolute value. If the limit of this multiplier's absolute value turns out to be less than 1, then something happens. And if it turns out to be greater than 1, then something happens. What are those somethings? Well, if the multiplier, or its absolute value anyway, is approaching something less than 1, then the series itself is looking more and more like a geometric series with a fixed multiplier that is less than 1. That's what's happening in the tail of the series. And since convergence is determined in the tail, then the result would be that the series converges. In fact, we can make a slightly stronger statement. The series converges absolutely. That's very nice. It means we can rearrange its terms without worrying about it converging to some other value or diverging or anything like that. How do we know that it converges absolutely? Well, that ultimately comes from the fact that we were looking at this absolute value right here. I spell it out in detail in the book if that basic intuition is insufficient for you, but I will refer you to that should you care to dig into every nook and cranny. Okay, but suppose we have our series, our non-geometric series, and we look at its multiplier, which is not constant, but in the limit it becomes constant, and it becomes something greater than 1. What do you suppose happens? Well, if that multiplier approaches something greater than 1, then in the tail of the series looks more and more and more like a geometric series whose constant multiplier is greater than 1. And we know that when that happens, the series diverges. And you may have noticed that I left one possibility out here. We talked about what happens when the multiplier approaches a value less than 1, or when it approaches a value greater than 1, but I did not say anything about what happens if it is equal to 1. Well, in the case of a true geometric series, not one that just looks geometric in the tail, but a true geometric series, if the fixed multiplier really is 1, then that geometric series would diverge, right? Because you'd have something like some constant a plus a plus a plus a plus a, because every time your multiplier is 1, so nothing is changing. And of course, if you had something like that, this will obviously diverge. If a is a positive number, the partial sums blow up to infinity. If a is a negative number, it blows up to negative infinity. Or would that be blows down to negative infinity? And, well, actually, if a is 0, then you'd have 0 plus 0 plus 0 plus 0 forever. So that would converge to 0. Although that's a bit silly because that's not even really really a series. You're just adding nothing forever, so there's no mystery what happens there. But anyway, in a true geometric series, a situation where the fixed multiplier was 1 would result in a divergent series. That's not necessarily the case when we're not looking at a true geometric series, but one that only looks geometric in the long run, because we have to worry about whether our multipliers are approaching 1 from above or below, and how fast they're approaching 1. It gets very subtle because 1 is the boundary that separates convergence from divergence. And when we are approaching that boundary itself in the limit, things can get tricky. And as you will see in the exercises, it could actually go either way. If the multiplier is not constant, but it approaches 1 in the limit, the series might diverge or it might converge, which means that if it's equal to 1, there's really nothing we can say about the series, at least not on the basis of this particular test. So if the magnitude of the multiplier approaches 1 in the limit, all we can say with this test is that the test is inconclusive, and you'll have to try some other method. And that's the ratio test. I hope it makes sense to you. It's actually very intuitive if you understand how it's related to geometric series. Oh, and I should add one little side comment about the multiplier itself. Namely, we can usually find the multiplier by staring and thinking, which is a time-honored method in mathematics, of course. But if that staring and thinking fails, we can find it algorithmically as follows. If the series is expressed this way, as the sum of a sub n, then the absolute value of the multiplier is the absolute value of the ratio a sub n plus 1 over a sub n. And I will explain where that comes from in a minute. But truth be told, if you understand the ratio test the right way, and you think about it in terms of multipliers, you may never need to construct that thing algorithmically. Staring and thinking may be all that you need. But of course, most textbooks are written in a way that tends to just teach algorithms, in part because, well, it's easy to teach someone an algorithm. It's a little harder to convey the intuition behind staring and thinking about the meaning of something. But that's what I'm going to try to do here. And as we do that, as I said, we'll see exactly where this comes from. It's very simple. And in fact, what the hell, I'll explain that right now. Since again, if you look in almost any calculus book, the ratio test will be described in terms of something like this. This is the ratio it's talking about. But anyway, where is it coming from? Well, if this is my series, a1 plus a2 plus a3 plus so on and so forth, so that the general term is a sub n, and I have my little stick man here again, and he's wondering what the multiplier is in this entire series, well, he's going to think about what the next term looks like. Well, in this general series expression, of course, the next term would just be a sub n plus 1. And then he thinks, well, what's the multiplier I need to get from a sub n to a sub n plus 1? That is, what do I have to multiply a sub n by to get a sub n plus 1? Well, think of it as a fraction. I ultimately want a sub n plus 1 upstairs, so of course I'm going to put it there. That's no problem. But if I just multiplied those two, I'd get a sub n times a sub n minus 1. I need to cancel this guy out so that I'm left with just the thing I want. But if I'm going to cancel it out, I have to put a copy of it downstairs. Then I get the cancellation I desire, and all is well. So of course, now we can see that the multiplier we need to go from a sub n to a sub n plus 1 is a sub n plus 1 over a sub n. That's my general multiplier for a completely general series, which is why it shows up right here. But it shouldn't be the kind of thing that you just memorize and apply algorithmically. You want to think about where it's coming from. And as I said, you usually won't even need it because you can just think about the multiplier directly and bypass some of this formalism. But I'll show you how it's done both ways. For our first example, let's test this series, whose general term is n to the 20th over 5 to the n, for convergence. And let's run through two different solutions. First, by staring and thinking, and then by taking the more traditional algorithmic approach. Okay, solution 1, stare and think. I'm going to try out this new gadget, this ratio test we've been hearing so much about. This series actually looks pretty promising for the ratio test because, as we'll see in some further examples, the ratio test works really nicely when n occurs in an exponent. It also works really nicely when we have things like n factorial in a series. And of course, you remember where those things show up all the time in Taylor series, which we will get to before the end of this lecture when we're talking about power series. But anyway, let's try our new ratio test out. This series is not geometric, of course, but what happens in the tail of the series? Maybe it starts to look geometric. Well, let's find out. I need to think of a multiplier. I'm going to try to do this simply by staring and thinking. What would the multiplier be in this case? Well, what would our little stick man say? The general term of the series is n to the 20th over 5 to the n. So he's got to think about what the next term is going to look like. The next term is, of course, very much like the previous term, except everywhere there's an n, there's now going to be an n plus 1. So that we have the 20th power of n plus 1 over 5 to the n plus 1. And what we have to think about is, what is the multiplier that will take us from the general term to its successor? Well, this isn't hard to see. As always, we will think about it in terms of a fraction. The bottom is a piece of cake. To get from 5 to the n to 5 to the n plus 1, I just have to multiply the bottom by 5. But how about the top? I need to get from n to the 20th to n plus 1 to the 20th. Well, that's not just a matter of tacking on an extra factor of something, but I can force the issue. I want n plus 1 to the 20th upstairs at the end of the day. Well, so I will put n plus 1 to the 20th upstairs in my multiplier. But that won't do it in and of itself, because if I multiplied this stuff by this stuff, I'd end up with n to the 20th and n plus 1 to the 20th upstairs. I need to get rid of that n to the 20th, which means I need to tuck a copy down into the basement of my multiplier. And that's it. That's my multiplier. Now again, I wrote this out with a little stick figure here, but after a while, and that while is very short, you won't need that. You'll just look at this thing directly and say, well, let's see, what's my multiplier going to be? Well, clearly I'm going to need a 5 downstairs, because I'll be going from 5 to the n to 5 to the n plus 1, and upstairs I'm going from n to the 20th to n plus 1 to the 20th. Oh, I see, so I need an n plus 1 to the 20th upstairs, but I need an n to the 20th to balance it out downstairs. Oh yeah, and I'm looking at the absolute value of the multiplier, so I better tack those on as well. And now we have an expression for our multiplier in absolute value. And I can use the basic rules of working with absolute values to simplify that a bit. I can think of this whole thing once again as 1/5 times all that other junk. And since the absolute value of a product is the product of the absolute values, I could rewrite that as the absolute value of a fifth times the absolute value of all that other junk. But of course, the absolute value of a fifth is just a fifth. And here too, something to the 20th over something to the 20th is the ratio of the two somethings to the 20th. And of course, if you raise anything to the 20th power, you get something positive. So the absolute values here aren't doing anything, and I can get rid of those altogether. And so now we have cleaned this up considerably. But again, I explained that in excruciating detail. After doing 2 or 3 of these, you see it almost immediately. Instead of spelling out every step there, you would just do them in your head automatically. You'd look at this thing and say, I'm pulling out the 1/5, then all this other stuff is n plus 1 over n, that quantity to the 20th power, which means I don't need the absolute value signs because I'm raising something to an even power. And you just write that down. So easy step, easy step. So what have I got? The multiplier, the general multiplier for this series in absolute value looks like this. Well, that's not a constant. Of course it's not a constant. It's only going to be a constant if you have a geometric series. This one isn't geometric, but does it look more and more geometric as we go? Well, let's find out. Let's take the limit of this thing as n goes to infinity. When we do that, what happens? Well, n plus 1 over n, that approaches 1 in the limit. So that means this whole factor approaches 1, which means this whole expression for the multiplier approaches 1/5 as n goes to infinity. But 1/5, what is that telling us? That's telling us that the deeper we go into this series, those multipliers, as we go from one term to the next, it's looking more and more like we're just multiplying by 1/5 each time. So it looks like a geometric series in the tail of the series. And the tail of the series is where convergence is determined. And a geometric series with a multiplier of 1/5 converges. So having shown that, we can just say, so by the ratio test, don't forget to state the test you're using, the series converges. In fact, if you wish to emphasize it, you could say that it converges absolutely, which in this case is obvious since all the terms are positive to begin with. But that's it. That's all the ratio test is. And I think once you get used to this notion of just staring and thinking, you will come to like it very much. But maybe I'm wrong. Maybe you don't like it. Maybe you just want an algorithm. So let's redo this same convergence test using the ratio test again, but instead of solving it simply by staring and thinking, we will solve it in the second style, which is a little more traditional, but I think it conveys less intuition for what's going on. So this will be our purely algorithmic solution. Okay, in this case, what we have is that we still want to find an algebraic expression for the multiplier. But maybe we don't like staring and thinking, so we're just going to say, okay, let me imagine that the series I'm working with is called a sub n. So I'll just remind myself here that a sub n is the general term here, n to the 20th over 5 to the n. What's the multiplier going to be? Well, I've memorized this algorithm. A to the n plus 1 over a to the n. And I want that in absolute value. Then I have to write that down. A to the n goes on the bottom. I know exactly what that is already. That's n to the 20th over 5 to the n. And what goes upstairs, that's a to the n plus 1. Okay, well, if this is a to the n, then a to the n plus 1 is its successor. That's the next term. That's when, instead of having n's there, we're going to have n plus 1's. So it will look like this. Yuck! See, this is what I mean. We have fractions within fractions. But never mind. Let's grind this out. We can do some basic algebra. We've got a fraction divided by a fraction. So, of course, we're going to invert and multiply, like so. And then we're going to do some simplification. So how does that work? Well, let's see. We'll end up with one fraction at the end. I've got 5 to the n upstairs and 5 to the n plus 1 downstairs. That's going to leave me with a 5 downstairs. Meanwhile, the rest of the stuff, n plus 1 to the 20th and n to the 20th, just have to sit there. And I've erased it, but if you go back and look at our first solution, this was what we came up to begin with for the multiplier. So of course we're headed towards the same place. And once we clean this up a little bit, we recognize that we could write this like this. And then we're still going to take the limit as n goes to infinity, and it's still going to go to 1/5. That's as n goes to infinity. And of course, this 1/5 is less than 1, so the series converges absolutely by the ratio test. Of course, we reach the same conclusion, but by staring and thinking, we at least cut out some of this ugly nonsense. But it amounts to the same thing either way. And I will say, even if you do it this second way, even if you take this algorithmic solution, even just this first little thing right here of writing what this represents, that it represents a multiplier, I think will help your intuition a lot. Typically, again, in most textbook treatments, you would just start here as though this were the mysterious subject of the sentence, and you're not really sure where it came from, except that it was just part of some strange algorithm. I don't think that helps. Whereas I do think beginning with the true subject of the sentence, what this thing represents, which is the multiplier in the series, helps you remember why this test works, which in turn helps you remember what the test actually says, because you certainly remember how geometric series work. Everybody remembers that. And so if you recognize that we're working with a multiplier here, then the rest is very natural. Okay, I mentioned earlier that the ratio test works pretty nicely for series where n appears in the factorial. So let's do an example of that sort next. But everything is a little cramped down here, so I am going to go ahead and clear the stage. So now in this more spacious atmosphere, let's introduce example 2, in which we will test this series for convergence, where the general term is 1000 to the nth power over n factorial. And let's just stop and dwell on those terms for a moment. The numerator grows incredibly fast. It's an exponential function with 1000 as its base. When n is 2, the numerator is 1,000,000. When n is 3, it's 1,000,000,000. When n is 4, it's 1,000,000,000,000. So you might think this thing is blowing up so fast that surely this series must diverge by the divergence test. Well, that's not true, because the denominator is n factorial, and factorial growth is even faster than exponential growth. It may not feel like that at first, because for small numbers, the top has a big head start. When n is 4, the top is 1,000,000,000,000. The bottom is only 4 factorial, which is 24. But as n gets larger, the factorial will catch up to the exponential, and then surpass it, and then leave it in the dust. So the general term does in fact vanish as n goes to infinity. But the presence of that factorial makes us think that the ratio test might be appropriate here. So let's try it out. Our first solution will be with our stare and think method. We want to consider an algebraic expression for the multiplier in this series. What is that going to be? Let's see if we can do this one a little more quickly without our stick figure there to help us. We're going to think of it in terms of a fraction. What will take us from our general term, 1000 to the nth over n factorial, to the next term? Well, the next term would be 1000 to the n plus 1 power over n plus 1 factorial. The top is simple. To get from 1,000 to the nth power to 1,000 to the n plus 1th power, we just need one more factor of 1,000. And how about downstairs? We're trying to get from n factorial to n plus 1 factorial. Well, n factorial is the product of the first n whole numbers. N plus 1 factorial is the product of the first n plus 1 whole numbers. But that product includes the product of the first n whole numbers, and then it has one extra factor of n plus 1. So all I need down here is n plus 1, and this is precisely the multiplier that takes us from the general term to the next term. And yes, I want this in absolute values, but strictly speaking, they aren't even necessary here because 1,000 is positive and n plus 1 is positive as well. So here's our multiplier in absolute value. Now all we have to do is take the limit as n goes to infinity. What happens as this goes to infinity? Well, the 1,000 just sits there, and the n plus 1, of course, blows up to infinity, which means the limit is 0. And since 0 is less than 1, the ratio test tells us that our series converges. Absolutely, in fact. And that's it. That's the complete solution. Now let's see a second solution where we just proceed algorithmically. Once again, we need to think about the multiplier, but this time we remember that form of the multiplier. I'll bring our stick man back, who remembers that the multiplier is a sub n plus 1 over a sub n. And here, a sub n, the general term of our series, is 1,000 to the nth power over n factorial. So that means our multiplier has precisely that as its denominator, while its numerator, a sub n plus 1, is the same thing if we replace those n's by n plus 1s, like so. All right, let's clean this up a little bit. We're going to invert and multiply and simplify what we have there. We have n copies of 1,000 downstairs and n plus 1 upstairs. So that means we're left with one copy of 1,000 upstairs. And here we have n factorial upstairs and n plus 1 factorial downstairs. Well, again, think about the meaning of the factorials. This is the product of the first n numbers. This is the product of the first n plus 1. And the product of the first n plus 1, of course, is the product of the first n numbers times one more factor, n plus 1. And so there is our expression, which should look familiar because, of course, we found that in our first solution as well. And now we will take the limit as n goes to infinity. And, of course, once again, we get 0. So by the ratio test, this series converges absolutely. And that's it. That's the way the ratio test works. You can do it with either solution style you wish. The two, of course, are logically equivalent, but I find the stare and think business to be psychologically much more pleasant. But it's up to you. But the time has come to put the ratio test to use in our study of power series, which is what we will discuss for the rest of this lecture. So, what is a power series? Informally, we would say that a power series is a polynomial of infinite degree. We are familiar with polynomials of finite degree, like this second degree polynomial in powers of x, or this third degree polynomial in powers of z, or this fourth degree polynomial in powers of x minus 2. So a polynomial of infinite degree would be like one of these whose terms kept going on forever. A more formal definition would be a power series centered at some particular value a is this stuff. More often than not, we work with power series centered at 0. Now, a power series centered at 0 would just have all of these a's equal to 0, so it would look like this. It's a polynomial of infinite degree in powers of x. If we had a power series centered at 1, it would look like this, an infinite degree polynomial in powers of x minus 1. A special case of power series, by far the most important case, is a Taylor series for a function centered at a. After all, a Taylor series itself is a polynomial in powers of x minus a, that could just be plain old powers of x, if we're looking at a Maclaurin series, of infinite degree. Now, the next thing to bear in mind is that a power series is, above all, a function. You can put numbers into a power series. We have those input slots everywhere there is an x, infinitely many of them. And then, once you have put a number in, you get a numerical infinite series out. And if it converges, the output of your function is the value to which it converges. So one big question we will usually need to ask when we have a power series is, what is the domain of this function? We want to know for which values of x will this produce a convergent series. Let's just go ahead and jump into an example and play around with these ideas a little bit. So the first problem that I will pose is to find the values of x for which this specific power series converges. Now this series, this power series, we see is centered at 4 because it develops as powers of x minus 4. And the coefficients are of the form n squared over 3n. There are infinitely many numbers we could stick in here for x. And when we stick any number in, we get a numerical series. For some of those values of x, we'll get a convergent series, and for others, we will get a divergent series. We want to find the values of x that make this thing converge. Now, if I just set you loose on this problem with no instruction whatsoever, the first thing you would probably do would be to just try out some different values of x and see what happens. And one thing that you would certainly discover very quickly is that when x is 4, this series becomes something very simple. Everything is the same here, except that where we had x, we now have 4. Oh, but that means I have a 4 minus 4 as one of my factors here. Well, that's a big fat 0, and 0 to any whole number power is still 0, so that means every term is 0. So that means I'm just summing up a bunch of zeros, which of course gives me 0. Aha! That means we have found one value of x that makes this power series converge. Well, only infinitely many more to check. And when I am playing with power series, I find it is very helpful to draw a little picture of the number line and keep track of where I have convergence and where I have divergence. So for example, I know that at 4, when x is 4, I get convergence. So I will put a little green dot there. And if I find that it diverges somewhere, I'll put a little red dot. Okay, so I know that this power series converged at 4, the very place where it was centered. And this is a general principle that always holds. Because if I look at any old power series, looking at the general expression for a power series here, if it's a power series centered at a, so that it develops in powers of x minus a, if I evaluate it at a, if I make all of those x's equal to a, I get lots of a minus a's, which are zeros, which kills every single term in the series except the constant term if there is one. So that means that when I substitute a in, the series will converge. So every power series converges at the point where it is centered. But anyway, let's just continue messing around and let's try one other point. When x is 10, this series becomes all of this stuff. At the place where we had an x before, we're just substituting a 10. But what happens? This 10 minus 4, of course, is 6. And then I have 6 to the n over 3 to the n, which I could rewrite as the quantity 6 over 3 to the n. So that's 2 to the n. And look at my series now. The general term is n squared 2 to the n. Well, that series obviously diverges by the divergence test. If we take the limit of the general term, it just goes to infinity. It definitely does not vanish. So that means on my number line here, if I were to go out to 10, I would put a little red dot there. I know I have divergence there. So letting x be 4 gives me a convergent series. Letting x be 10 gives me a divergent series. Well, that's 2 down and still only infinitely many to go. Obviously, we cannot proceed in this manner. We need to find a way to test infinitely many points at once. And guess what will allow us to do that? Yes, you guessed it. It is the ratio test. So now let us approach this in a more systematic manner. Power series are made for the ratio test because they all involve this thing right here where n appears as an exponent. So let's go ahead and write down the multiplier to this series and see if it behaves like a geometric series in the long run. The multiplier is going to be what? Well, we're trying to get from this general term to the next term. Let's see if we can just write it down all at once. Well, we always think of it in terms of a fraction. Think about the pieces. What will they look like in the next term over? Let's start with easy stuff. 3 to the n in the next term is going to be 3 to the n plus 1. We'll have one extra factor of 3. That means in my multiplier, I'm going to need to have a 3. I have to multiply by 3 once. And how about the n squared? This one we have to be a little more careful about because in the next term, that's going to be the square of n plus 1. Okay, so I'm ultimately going to want the square of n plus 1, so I'm just going to put an n plus 1 squared in there, but of course I'm going to have to balance out that n squared, so my multiplier should have an n squared downstairs, so that when I multiply this general term by this thing, those n squareds will cancel, and I'll just be left with the n plus 1 squared upstairs that I actually want. Okay, and then I have this x minus 4 to the nth power. Well, in the next term, I would have x minus 4 to the n plus first power. So that means I just need one more factor of x minus 4. And that's my multiplier. I do want it in absolute value, as the ratio test requires, because it's based on geometric series where we're looking for, of course, the absolute value of the multiplier. And now let me just rewrite this in a slightly cleaner form. Using familiar properties of absolute values and exponents for that matter, we can rewrite this as this stuff. Note that the x minus 4 has to remain an absolute value because there's no way of knowing whether x minus 4 is positive or negative. For certain values of x, it will be positive. For certain values, it will be negative. The square of anything, however, is always positive, so I don't need the absolute value there. And of course, 1/3 is positive, so I don't need it there. But anyway, what is this stuff? This is the absolute value of my multiplier. Well, so I want to know what happens to it in the long run. As n goes to infinity, the only part that depends on n is this stuff right here. The rest is just going to sit there because it is not dependent on n. And in this case, n plus 1 over n, of course, it goes to 1 in the limit. So that whole factor goes to 1. And that means that all this stuff goes to 1/3 times x minus 4. Now, why do I care about that? This is, in the long run, what the multiplier looks like. So if this thing is less than 1, my series will converge. So by the ratio test, don't forget to cite the test you're using, this power series converges, absolutely in fact, when 1/3 of the absolute value of the quantity x minus 4 is less than 1. That is, when the absolute value of x minus 4 is less than 3. Now we've basically got it. Just a quick reminder down here in the dungeon. When we have the absolute value of a difference, which is the kind of thing that shows up all the time when we're doing these sorts of problems, when we have the absolute value of a minus b, that represents the distance between a and b on the number line. Thinking about that helps us interpret inequalities like this very easily. We know the power series converges absolutely when the distance between x and 4 is less than 3. Well, look, here's 4. If the distance between x and 4 has to be less than 3 to have convergence, that means x can only go 3 units to the left or right from 4. So I could go as far out as 7 on one side, 3 up from 4, and as far down as 1 on the other, 3 down from 4. And what we've just shown is that our power series converges for all of the infinitely many values that lie between 1 and 7. We got them all at once. So let me put them all in green. And the ratio test has just shown its power by establishing convergence at infinitely many points simultaneously. A few thoughts here. First, the ratio test also gives us a lot of information about where this series diverges. We usually don't write this step out for reasons that I will explain very soon, but just to make sure you understand where it comes from, let me just add something in here temporarily. The ratio test also tells us that the series diverges when the multiplier is greater than 1. But again, let me multiply both sides by 3 to turn that into the distance between x and 4 is greater than 3. When that happens, we know the series diverges. Well, what does it mean for the distance from x to 4 to be greater than 3? Well, here's 4. If we're more than 3 units away, we are either beyond 7 to the right or beyond 1 to the left. So I could put all of that stuff in red. So now we have an almost complete picture. We still haven't said anything about convergence at these two special points, 1 and 7 themselves, and we'll get to that in a moment. Now, I mentioned earlier that in practice, we usually don't add this step about where it diverges because what happened here, more or less, happens every time we look at a power series. We will always find that a power series converges obviously where it's centered, and then it converges on all points in some interval surrounding that center, where it's the same distance to the right and to the left. And that little distance, 3 in this case, is called the radius of convergence. So in this case, our radius of convergence is 3. And once we have found that radius of convergence, we know that the power series will always diverge beyond that. So we don't actually have to put that step in there. But in every power series, the convergence will take place on what we call that power series's interval of convergence. And in fact, the way that a problem like this would usually be posed is not find the values of x for which the power series converges, it would usually be posed as find the interval of convergence for this given power series. But as I said before, we're not quite done, because I haven't said what happens at 1 or 7, because those are the values of x that would make this thing, our multiplier in the limit, equal to 1. And we know that the ratio test tells us nothing when the multiplier is 1 in the limit. So we are going to have to investigate the endpoints of our interval of convergence separately and individually. This is always the last piece of the puzzle. So let me erase this last line, which, as I said, in practice we don't include. Now we'll check for convergence at the endpoints of this interval. So first, when x equals 7, let's start on the right, this series becomes, well, here's our series. When we pop 7 in for x, it becomes what? Well, all this stuff just comes down, but where we had x minus 4 to the nth, that's now going to be 7 minus 4 to the nth, which is, of course, 3 to the nth. But now I've got a 3 to the nth upstairs and downstairs, so they cancel out, and I'm left with the series whose general term is n squared. And that series, obviously, diverges by the divergence test. The general term blows up to infinity. So that means at 7, I can go ahead and fill in that hollow point with a red dot. I know it diverges there. What about at 1? You might wonder if it has to work out symmetrically, that if it diverges here, it has to diverge here, or if it converges here, it has to converge here. No, it doesn't work like that. Sometimes you get the same convergence status at both endpoints, sometimes you do not, so we have to check every time. Let's see how it works here. When x equals 1, we get what? Well, the usual stuff, but then where we had x minus 4, that's going to be 1 minus 4, which is minus 3. That is getting raised to the nth power, and I can rewrite that stuff because I've got minus 3 to the n over 3 to the n. Well, that's the quantity minus 3 over 3 to the n, which is minus 1 to the n. Well, let's look at this series, whose general term is n squared, but then I've got this minus 1 to the n, which means that it's flipping back and forth from positive to negative. But the magnitudes of the terms are getting bigger and bigger and bigger because of that squaring. So at any rate, they are definitely not approaching 0. So this one too diverges by the divergence test. So there too, where I have that hollow point, I can fill in a red dot. And now I have my full picture. Now I need to write up my little summary at the bottom. So the interval of convergence, let's use that terminology, for this series is from 1 to 7 with rounded parentheses there. Hopefully you are all familiar with that kind of interval notation, but if you are not, just a quick reminder, if we intended to include an endpoint, like if we needed to include 7, we would put square brackets to indicate inclusion. The rounded parentheses mean up to but not including. And that's it. Our problem is finished. A few quick thoughts before we look at a second example. One is that sometimes our interval of convergence will turn out to be an infinite interval of convergence, stretching from minus infinity all the way out to infinity. We'll see an example of that soon. That would be a power series that converges for all values of x. Those are very nice. The other thing I should point out is that when we came up with our multiplier here, we could have done it in the more typical textbook algorithmic style rather than just staring at this thing and thinking about what the multiplier had to be. And if we were going to do that, that would be fine, but our work would have looked something like this. We'd be looking for the multiplier's absolute value, and then we'd have to think, back to that thing that we memorized, how do I get that? Oh yeah, if the series looks like this, then we take an plus 1, the successor of the general term, and divide it by the general term, and that's the thing I want. So in this case, what would go here? Well, let's see. The general term goes downstairs, so that would be all of that stuff. So let me shove that down there, and then its successor goes up here. That would be the same thing, except everywhere I have an n, which is in 3 places here, I'd need an n plus 1. So it would look like this. Yuck. And I will leave you the joy of cleaning it up. But when you do, you will find, of course, that it works out to precisely this stuff right here. And then you take the limit as usual and everything would proceed the same. So you're perfectly welcome to use this way of doing it if you like. Sometimes it can be helpful if you feel like you're getting a little confused. But for the most part, I think it's easier just to stare at it and think about it. Choice is yours. Expressions like this just make me antsy, so I do what I can to avoid them. But I think it is time for us to turn to a second example. let us find the interval of convergence of the Maclaurin series for the exponential function e to the x. That's the Taylor series centered at 0, and of course everybody knows what that series looks like. So how will we do this? Well, a Taylor series is just a power series, and we approach all power series the same way. We use the ratio test, so we're going to need to look at our multiplier. Well, what's that going to be? Let's just stare and think about it. To get from the general term, x to the nth over n factorial, to the next term, which of course would be x to the n plus 1 over n plus 1 factorial, what must we multiply by? Well, think of it as a fraction, as we always do. When we go from any term of this Taylor series to the next term, we pick up one extra factor of x upstairs. So of course, that's going to happen here as well. To go from x to the n to x to the n plus 1, we're just picking up one extra factor of x, so we need an x upstairs. And downstairs, every time we move up a term, we increase that factorial by 1. But to go from, say, 2 factorial to 3 factorial, that means just multiplying by 3, because we already have 1 times 2. So we need to multiply by 3 to make it 1 times 2 times 3. And to get to 4 factorial, well, we already have 1 times 2 times 3, so we just need to multiply by 4 to get 4 factorial. And to get from n factorial to n plus 1 factorial, well, we already have the first n factors. We just need an n plus 1 as well. So we are going to get an n plus 1 downstairs. And that's it. That's our multiplier. If we take our general term and multiply it by that, we will get the successor to that general term. Of course, we want it in absolute value, which we have to take account of because x might be negative. Anyway, what is this multiplier doing for us? We want to think about what it looks like in the limit, in the long run, as n goes to infinity. So we're going to take that limit right now. What happens as n goes to infinity? Well, x just sits there, but the denominator, n plus 1, blows up to infinity, eventually swamping x, whatever it may be, which means that the entire fraction goes to 0 as n goes to infinity for all values of x. That is, if we're thinking about the number line, and we have our series centered at 0, no matter what value of x we stick into our power series, we're going to get some kind of numerical series as a result. And we know that no matter what that x was, the multiplier in that numerical series is going to approach 0 in the limit. And 0 is less than 1, so by the ratio test, the series for e to the x converges absolutely for all values of x. Thus, the interval of convergence is from minus infinity to infinity. The entire real line, which means there are no endpoints to check this time. And by the way, this result explains something we saw all the way back in the beginning of the chapter, and we were just talking about Taylor polynomials. We saw that as you increase the degree of the Taylor polynomial for e to the x, the Taylor polynomial seemed to approximate the function over a wider and wider range as the degree of the polynomial increased, and it looked like there was no stopping it. That by increasing the degree higher and higher and higher, the Taylor polynomials would hug the graph of e to the x over a ever-increasing domain. Well, now we see why that is so. It's because if we increase the degree to infinity to get a full Taylor series, we'll get convergence everywhere. So that's that. If you don't like the stare and think method for coming up with a multiplier, you could have done this one in the more traditional color by numbers approach, where you remember the recipe, and then you say a sub n. That's the nth term. Oh, that's this guy. So the general term goes downstairs, and upstairs is the successor of this term. So that's going to be this term where we turn all the n's into n plus 1s, like so. And now we can begin to go through the usual algebraic shenanigans, leading us eventually to, of course, the place where we started over here. No problem if you want to do it that way, but again, I like this way better. But hey, you are not me, so make your own decisions. Just be sure you understand what you're doing, and that either way, you are simply computing a multiplier and considering what happens to it in the long run, so that you can relate everything back to geometric series. Let's look at a third example. Let's find the interval of convergence for this power series. Where on the real line does this thing converge? Well, it is a power series in powers of x, so we know it is centered at 0. Obviously, it converges at 0. If you pop 0 in here, this thing sums up to just plain old 1. But where else? Well, it's easy to find out, because we approach all power series the same way, which is through the ratio test. So we're going to look at the general multiplier for this term. Well, we're going to build up our fraction. We have nothing but ones in the numerator, so nothing is getting multiplied up there, but the denominators are increasing from 1 to 3 to 5 to 7 to 9 and so on and so forth. With each successive term, we get the next odd number. So how do we deal with that algebraically? Well, in the general term, the denominator is 2n plus 1. So what would the denominator of the successor term be? It's not 2n plus 2. We're not increasing it by 1. We are increasing it by 2 every time. So in the next term, the denominator would be 2n plus 3. So what do I have to multiply this by to get a 2n plus 3 downstairs? Well, we do the usual trick. I'm just going to go ahead and put 2n plus 3 where I want it, but to balance out that 2n plus 1, I'm going to need to put that upstairs. That way, when I multiply this guy in the general term by this multiplier, the 2n plus 1s will cancel out, and I'll just be left with a 2n plus 3 downstairs, which is what I want. Great. So that takes care of those odd numbers in the denominator. But I also have to deal with my x's. Well, that's really easy, because for each successive term, I just pick up one more factor of x. X to x squared, to x cubed, x to the fourth. I'm just multiplying by x each time. So of course I'm going to get a factor of x in my multiplier. And we have it. There is our multiplier. Now this first factor right here is always positive because n is always positive. So I'm going to go ahead and pull that out. And now why am I looking at this multiplier? Of course, because I'm thinking about what happens to the multiplier in the long run. And when I take the limit of that multiplier expression as n goes to infinity, what happens? Well, the absolute value of x just sits there, but this junk up front, 2n plus 1 over 2n plus 3, that just approaches 1. So that means the entire expression goes to the absolute value of x. So what can we deduce from that? Well, the ratio test, which is just built on the geometric series test, tells me that we get convergence when this value is less than 1. So by the ratio test, the series converges absolutely when the absolute value of x is less than 1. Aha! That tells me that in my picture, I can go up to 1 and down to minus 1, and I know that everywhere in between, we get convergence. If I pop 0.612 into that series, I will get a convergent series. If I pop minus 1.43 into that series, I will get a divergent series. But I don't know what happens if I pop minus 1 or 1 in there. So let's investigate those next. When x is 1, the series becomes, well, if we let x equals 1 there, we get this series. And what do we know about that series? Well, let's just think about it intuitively. In the long run, that series is going to behave the same way as the series whose general term is 1 over 2n. And that series, well, I could pull that half out and it's going to behave the same as this series. Oh, but that's the harmonic series. So intuitively, it's clear that this thing is going to diverge. It's going to stand or fall with the harmonic series itself. And if I wanted to nail that down with a little more rigor, and let's do that, we would say that this series diverges by limit comparison with the harmonic series. So I'll write down that when x equals 1, the series becomes this thing, which diverges by limit comparison with the harmonic series. But at any rate, when x equals 1, our series diverges. So I will put a little red dot in there to remind me. And we still have to check the other endpoint, which is when x is minus 1. And when that happens, the series becomes this fine fella. Oh, this is an alternating series. And in fact, the magnitude of its general term vanishes as n goes to infinity, and vanishes monotonically at that. So the series becomes this series, which converges by Leibniz's test for alternating series. So when x equals minus 1, we get convergence of our power series. And this is a nice example where we have some asymmetry in our endpoints, convergence at one and divergence at the other. Thus, the interval of convergence for this particular power series is from minus 1 to 1, where the minus 1 is included, but the 1 is not. Hence the square brackets on the minus 1 and the rounded parentheses on the 1. Again, if you don't like the stare and think method for finding the multiplier, you could have done it here in the usual textbook way, and of course, you would end up with the same thing that we obtained by staring and thinking. But that's it for this revised video. Good. It was a long one. See you next time.